Hello everyone, good morning. I'm Chen from UT Austin. Today I will present Unum and discuss a new way to rethink network control. This work is supported by Learning-Directed Operating System Expedition. So today, many network control actually shares a very similar architecture. It has a state estimation component that takes in the existing network signals and then tries to summarize what is the current system context. And then a controller takes the state representation and then make a decision. For example, in TCP BBR, it has a path model to estimate the bottleneck bandwidth as well as the main RTT. And then the BBR state machine takes these estimates to adjust the sending rate. For example, in MPC-based video streaming algorithm, it has a throughput predictor that estimates the future bandwidth. And also together with the buffer occupancy information, the MPC algorithm takes it to adjust the next bit rate. In all these cases, the quality of network control actually hinges on the quality of state estimation. And today, there's been a lot of recent work that has tried to improve network control by using machine learning. And in these systems, the main idea is to replace the controller logic with a learned model. For example, learned controllers like Orca and Pensive, what they're doing is replacing the controller with a deep reinforcement learning agent. However, the state estimation here is still relying on manual feature engineering. And this way of state estimation today is fundamentally limited. Let's just take a look at Pensive's throughput predictor as an example. It simply uses some local features, such as the video chunks throughput, which is size divided by elapsed time. And then it outputs a handcrafted aggregation, which is a rolling average across the past few video chunks. There has been a lot of other examples of these handcrafted aggregations in other network control. For example, directly using instantaneous values, using max or min or percentiles. And these simplistic representations using hand aggregations are actually not considering a lot of rich context in the network. And this leads to two fundamental issues. First one, the state you're observing is fundamentally delayed, because all these signals are derived from past observations, which are delayed by at least one or more RTTs. And then the controller is always reacting to the stale information. The second problem is that these representations have very poor representation power because they're missing a lot of latent factors in the network. For example, application level dynamics or controller interactions. And with these, even a powerful or learned controller is constrained by a weak and incomplete view of the network state. In fact, this poor state estimation has already hurt decision quality in practice. We ran a state-of-the-art learned congestion controller, Orca, on a real-world cellular trace. And you can see this graph is showing the send rate, how this orange line send rate is changing. And the background blue area is the actual real capacity. What we observe is that this red line is consistently underutilizing the actual available capacity, with an up to 50% of utilization gap. This motivates our key question: how to build better state estimation to improve network control? In this talk, I'll first give a very high-level overview of how do we model the network state. And then, with that, how does it lead us to rethink network control? In the end, I'll also introduce some key evaluation insights. For the first question, we realized that network state estimation is inherently a sequence modeling problem. We observe a time series of network observations, and then what we want to build is a representation that captures the underlying latent context and is predictive of future network state. To do this, we draw inspiration from today's large language model foundations. Transformers are particularly good for modeling complex sequences because of these orange multi-head attention boxes. It is able to capture long-range dependency and can uncover the latent factors that actually drive the future behaviors. So we train an encoder-decoder-based transformer using a next window prediction objective. The encoder takes in all these time series of observations, and the output of the encoder serves as a latent representation for the current network state. Since now we're using this learned attention to replace the original handcrafted aggregation, this provides a more accurate representation. Another key difference in our framework is that we are trying to learn from global features instead of just task-specific local features. We use the network features from a lot of different diverse applications, cross-policies, and also diverse network environments. And this allows the model to move from local signals to some global understanding. As a result, this learned embedding captures the latent factors that matters for an accurate prediction of a global state. Going to the details of Unum's design, in the paper we discussed a lot of other design choices, for example, for data collection, for token representation, for model architecture, and for training objective. Here I just want to quickly highlight one key insight we found. So a very straightforward way of modeling this future network state prediction problem is through regression. However, it is unbelievably hard. And what we realize is that the exact numerical values of future states doesn't really matter for a lot of network control tasks. What really matters is some threshold-based triggers. For example, when the queue is building up or when the bandwidth is sufficient. Building on this insight, we turn the regression problem into a classification problem where we bucketize each signal into some reasonable ranges and then train the model to predict which bucket the future states fall into. In practice, this actually improves the prediction accuracy by a lot. So let's take a look at the CDF of the average distance between predicted and true buckets. What we find is this orange line of classification transformer has improved the prediction accuracy by a lot. With an acceptable accuracy, if we're considering two buckets indexes of error, the classification-based approach can achieve up to 50% higher accuracy. And with this embedding, the next question is, how do we rethink network control? In control theory, there is a classical principle called separation principle. What it states is that an optimal feedback controller can be decomposed into two parts. The first part is an optimal state modeler. And then with that, the deterministic controller can take its state representation and make decisions. The previous insight of how to build an accurate state representation allows our framework Unum to instantiate this principle. And it's a fundamental refactoring of how we design network control. So this is how today's network control works today. And instead of tightly coupling the state estimation and control inside each network controller, we're proposing to design network state estimation as a service and also a first-class system component. The state estimation component, which is shown in this orange box, it learns a shared high-quality representation and exposes it to all the controllers. It enables implicit coordination across controllers because during training, the network data already reflects a mix of different controller behaviors and workloads interacting in the same network. As a result, this learned embedding models the effects of controllers, and we already understand how they act in the system. So when we feed this embedding back into the controllers, it can implicitly reason, for each controller, it can implicitly reason the presence and the behavior of other controllers. With this architecture, we're also simplifying controller design. By decoupling state estimation from the controller design itself, the controller is no longer to need about feature engineering, and they can focus purely on what is the control logic. The next question is, with this framework, how do we actually integrate Unum into existing already built controllers? And we've designed 3 dropping approaches for both heuristic controllers and learned controllers. For learned controllers, the most straightforward way is directly reaching the model using our Unum embedding. However, in practice, this is often infeasible and super expensive. Training pipelines are extremely complex, and there is often maybe the original data is not even available. So we also introduce an alternative approach, which is introducing an adapter network, which is a very lightweight MLP model. And this adapter network takes in the original controller's decision, as well as Unum embedding. Note that here, the original controller also has some local state estimation logic. But this adapter, it is augmenting it with some global context from Unum. And then it can correct the original controller's decisions when needed. For heuristic controllers, we also introduce a very simplified way of integration. We can directly replace their originally used historical observations or handcrafted state estimations with Unum's predictions. For example, in BBR, the controller estimates bottleneck bandwidth and main RTT from the historical throughput and historical delay measurements. And what we do is just simply replacing these with Unum's predicted throughput and delay, providing a more accurate and timely estimation of the network state. We implement Unum in user space, and we use eBPF hooks to get updates from the network events. And these signals are then streamed into this orange box, which is Unum's state estimation module. And this module runs asynchronously from the control loop. As we will show later, this async does not affect the quality of decisions too much, and it avoids adding latency to the critical path and allows state estimation to continuously improve in the background. We evaluate Unum in two use cases, congestion control and video streaming. And we compare it against learned controllers like Orca and Pensive and also heuristic congestion controller BBR. And all these experiments are in real-world emulations with real-world traces. What we find is that integrating Unum consistently improves performance. For learned controllers like Orca and Pensive, we see a 13% of test reward improvement for Orca and a 45% of improvement for Pensive. And for heuristic control with BBR, we maintain a similar throughput utilization while having a 22% of reduction in average queuing delay. Here I want to highlight a few interesting findings in our evaluation. This plot is showing how the training reward over epoch changes for our two integration approaches for learned controllers. And there's a clear trade-off here. This purple line of full retraining approach, it can reach a higher reward in the end. That's because it is actually optimizing the entire controller space together with Unum's embedding. But then this orange line of adapter approach, it is much easier to train. As you can see, the reward goes to super high from the very beginning. That's because what you're training is a super small model. And instead of retraining the entire full controller, it learns how to adjust the recommendations from an already trained controller model. We also study the impact of context length. The original Orca model takes in 10 RTTs of history. And then when Unum is trained with the same length, which is 10 RTTs, we can see that it improves Orca's reward by 13%. But when Unum only sees 5 RTT of context, performance actually degrades. We also want to see where does Unum gains come from. And what we find is that these mainly come from the compact representation provided by Unum's embedding. So for Pensive Unum, the Unum embedder takes in raw network signals and then outputs a compact embedding, which is then fed into a small MLP adapter. This original Pensive model has 2.5 million parameters, and together the embedder and the controller adapter has a total of 1.6 million parameters. And there they achieve 40% of improvement over the original Pensive. We also train an alternative architecture, which is directly taking in the raw network inputs and train a controller adapter. In this case, the performance is actually consistently worse than Pensive until we increase the model size, increase again and again, until the model size reaches 6.4 million parameters, which is 4x of what is used in Pensive Unum. And then it achieves 60% of improvement over Pensive. This is very interesting because what we get from Unum is already there in the raw data. But it is not easy to directly extract it from the raw data. And Unum's embedding acts as a very structured and compact way that makes the relevant signals easier for the controllers to learn, and leading to significantly better performance with much lower compute cost. We also quantify the decision delay of Unum. And note that all the measurements here are completely on CPU, no GPU is involved. And the decision delay is dominated by the model inference. What we can also see from these two graphs is that encoding layers is contributing most to the overhead. And with our default configuration, which is highlighted in the orange box, we have 4 encoder layers and 16 embedding size. The average decision delay is only 2.68 milliseconds. And despite this delay, the performance impact is minimal. We try different delays on Orca Unum and see that with the current delay, Orca Unum is able to preserve 96% of its performance compared to an ideal no delay setting. To conclude, Unum introduces a state estimation as a service, transformer-based global state embedding, and also lightweight controller integrations. It is a clean architecture where we introduce this shared state layer that captures rich cross-layer latent signals. And we believe this layer or this architecture is reusable across different subsystems because it can enable simple applications and more robust context-aware infrastructure. Unum is already open source, and we love you to try it out. And finally, I'll be on the job market next year, so feel free to reach out. Thank you.